here I'm looking at when is this equal? And I've got to break this problem into two problems. So I'm going to start by separating out my piecewise function. So 2x plus 3 when 2x plus 3 is greater than or equal to 0, and minus 2x plus 3 if 2x plus 3 is less than 0. Which implies, well, we're simplifying this. We get 2x plus 3 if x is greater than or equal to minus 3 over 2, and minus 2x minus 3 when x is less than minus 3 over 2. And I'm going to leave this as an exercise. But from here, we can now break it up into our two subproblems. And our two subproblems are going to be 2x plus 3 equals 2 minus x, and x is greater than or equal to minus 3 over 2. And minus 2x minus 3 equals 2 minus x, and x less than minus 3 over 2. Now I'm going to solve these two problems individually. When I've solved these two problems, I take the union of their solutions. So here, I need to solve the two inequalities individually. So here I get 3x plus 1 equals 0, or x equals minus 1/3. And here I have x is greater than or equal to minus 3 over 2. Taking the number line, our first answer gives us a point at minus 1/3. And our second example, if we go to minus 3 over 2, it's everything above it. Intersecting these two gives us a single point, because there's only one point over which both are satisfied, and it's just at the point x equals minus 1/3. What about this side? Well, here we have minus x minus 5 equals 0, or x equals minus 5. And here we have x strictly less than minus 3 over 2. Again, I take the intersection of these two constraints. My first constraint is a single point at minus 5. And my second constraint is strictly less than minus 3 over 2. For this problem, I take the intersection. Drawing my two lines, I get a single point at x equals minus 5. Well, these are the two subproblems. Remember, the last step we need to do is to take the union of the solution sets for our final problem. And our two solution sets are minus 1/3 and minus 5. Unioning these, we get minus 5 and minus 1/3. We're actually going to go through this suggested exercise. Now here, this suggested exercise incorporates both our absolute values and our multiple bounds. Now there's two ways we could do this. We could first split the absolute value into two functions and then look at the two different bounds. Or we could split the two different bounds first and then incorporate our absolute value into both. I'm going to first split our function into two different bounds, and then I'm going to split the absolute value, creating a total of 4 problems. But you can also do it the other way, where you split the absolute value function first and then split the multiple bounds. So here, what I'm going to do is I'm going to start by splitting it into 2, and I'm going to give myself lots of space here. Lots of space. So I have absolute x minus 2 is less than or equal to 3. And here I have absolute x minus 2 is greater than or equal to 1. So now that I have my two subproblems, I'm going to break this absolute value function into two pieces. So it's going to be absolute value of x minus 2 equals x minus 2 if x minus 2 is greater than or equal to 0, and minus x minus 2 if x minus 2 is less than 0. Now here, if I create my chart, my split point is 2. I have function x minus 2 giving me positive, negative, 0, 0, positive, negative. Using this chart, we can then update this function both by simplifying and updating a nice bound in terms of x. Get x minus 2 if x is greater than or equal to 2, and 2 minus x if x is less than 2. So with that work, we get 2. Remember, we're going to split it now into 2 additional inequalities. We have x minus 2 less than or equal to 3 and x greater than or equal to 2. Now we have 2 minus x less than or equal to 3 and x less than 2. Okay. Over on this side, we have the same sort of problem. It's the same absolute value we're splitting, but we're splitting it into 2 subproblems based on positive and negative. So we get x minus 2 is greater than or equal to 1, and x is greater than or equal to 2. And we also have x minus, or 2 minus x is greater than or equal to 1, and x is less than 2. So now we've got to solve each of these 4 problems individually. Okay? I'm just going to extend this line down. So to solve this problem, this gives me x minus 5 is less than or equal to 0, which my split point is 5. X minus 5 is going to be positive, negative, and I'm 0 at 5. So positive, negative, and x minus 5 is less than or equal to 0. So this is going to go from 5 downward. Or in this case, it's going to be x is less than or equal to 5. But we're going to write this as in interval notation as x is in the interval minus infinity to 5. And here, this is already an interval, or x is in the interval 2 to infinity. Because of this and, I need to intersect these 2 lines. I'm going to take 2 number lines. I'm going to draw minus infinity to 5. And I'm going to draw 2 to infinity. Using blue, I'm going to draw my key points. Again, this is 2 and this is 5. So my interval is from 2 to 5. So x is in 2 to 5. Now over here, I need to analyze this expression. So here, I get x is greater than or equal to minus 1. Or let's use our split point technique. So here, bringing everything over to one side, we get x plus 1 is greater than or equal to 0. This, we can create a chart. Our split point is minus 1. We have x plus 1. I know that I am at 0 here. I am positive, negative. So positive, 0, negative. I want to be greater than or equal to 0. So I include this point and forward. So x is in the interval minus 1 to infinity, and I include minus 1. Whereas here, this is the same thing as x is in the interval minus infinity to 2, non-inclusive. Drawing my number lines and inputting these intervals, I get minus 1 positive and minus infinity, not including 2. Drawing vertical lines at each of these key points gives the interval 0 up to but not including 2, or x is in minus 1 up to but not including 2. And here, these, we should be careful, these are square brackets because we include both 5 and 2. And now, before we combine this subproblem with this subproblem, we have to finish the absolute value. And remember, with our absolute values, what we're going to do is we're going to take the intersection of these 2, or the union of these 2 intervals. So we have our two intervals for each subproblem. And we go from, our first interval is from 2 to 5. And our second subproblem is from -1, not including 2. If we draw our key points, -1, 2, and 5. Remember, we're taking the union of these intervals. So we go from -1 up to and including 5. So here, for this problem, x is in the interval -1 to 5. Now over on this side, we have a similar split, and we can actually use the split that we have a similar problem, we have a similar process. We can't use the sign charts that we created over here, but we're going to do something similar. So we have our x -3 greater than or equal to 0. We create our split point at 3, x -3, this being positive, negative, or a 0 at 3, positive, 0, negative. My equality is greater than, so I include 3 and go further. X is greater than or equal to 3. So, and here we have x is greater than or equal to 2. So taking these two inequalities and intersecting them, we get 3 and bigger for our first, and our second is 2 and bigger. When I intersect them, I look at the key points for each of my lines, and I take the and, or both, which is 3 and positive. So x is in the interval 3 to infinity. Over here, we've got x -1 is less than or equal to 0. My split point is 1. I have x -1. Completing my sign chart, I have a positive, negative. I'm at 0 at 1, positive, 0, negative. And solving this sign chart, we want to be less than or equal to 0. So we're at the point 1 and below. So this is x less than or equal to 1. And here I have x strictly less than 2. So I can combine these two intervals. And remember, because it's an and, we're taking the intersection. So I have 2 and below. I have 1 and below. At 2, I'm an open circle. At 1, I'm a closed circle. So it's less than 2 and 1 and below. I draw a vertical blue line at each of these key points. And my intersection is going to be the interval 1 and less, or x is in the interval -infinity to 1, inclusive. I now take the union of these two intervals to complete my absolute value breakup of my function. So I have an absolute value at my first interval is from 3 onward. My second interval is from 1 and below. And I'm going to take the union of these. I have my key points, and we can see that the union is going to be from -infinity to 1 and from 3 to infinity. So x is going to be in -infinity to 1, union with 3 to infinity. Oh, that should be a round bracket. Infinity is not a number. Now, I've dealt with both of my absolute values, but remember, we split this up into two pieces because I had two bounds. So in order for 2 bounds, both of these conditions must be met. So I now need to take my resulting interval, my first interval and my second interval, and I need to intersect them. So the last step that I must do is that I must take these two intervals and intersect them. My first interval is I'm going from -1 to 5. My second interval, infinity to 1, 3 to infinity. And I'm intersecting them. So I take my key points. Remembering that these points are 1 and 3. And now I'm going to take the points that cover both. -1 is in both, up to 1 is in both. The bottom interval is not in both. And now I go from 3 to 5, which are in both. And my final interval is x is in -1 to 1, unioned with 3 to 5. And this is my final interval. So this is the set of x values that satisfies the constraint.